All right, my blueberries. Today we are going to fill out the other side of our equation sheet, and that is your assignment for this week. Is you need to make sure you have both pages filled out for your cheat sheet for your AP test, and then you need to make sure you send a picture of them to me so I can give you points for that. Only like half of you did it last week. So please remember the AP test is mandatory. It's not optional. There are consequences if you miss your AP tests. If you have questions, email me. So please make sure you're actually taking this seriously. They're gonna make sure you take your AP test and stuff. Yeah. So far we have talked about dynamics, which is a fancy schmancy word for forces. We've talked about energy and momentum, and that's probably gonna cover about 50% of your test. The other really big chunks that we want to really focus on here are kinematics and then torque and rotational motion. I'm going to kind of rearrange this a little bit. I'm going to put the simple harmonic motion and the universal gravity together, and I'm going to take circular motion and put it where I think it belongs, which is with the other stuff that spins. So the universal gravity and simple harmonic motion part is probably like 4% of the test. I hope it's not important because we honestly didn't spend a ton of time on simple harmonic motion. Like we kind of talked about stuff. We talked about energy. We did an AP practice question where we talked about a spring kind of oscillating back and forth, and there was some friction, so it slowed down, right? We talked about some stuff like that. It's stuff like that, but there are some equations that we'll go over today just to make sure you have them and you see them, and we'll talk about how they work. But we're going to spend most of the time on the kinematics and then the torque and rotational motion stuff, okay? So in case you don't have it, here's my filled out version of the first page, the 3 big tools that you really want to understand. So here's forces. You could pause it right now and copy that down. Here's energy. I'm not going to read the whole thing to you because you can pause it and read. You could take hours to read it if you felt like it. So pause it, copy that if you need it. And then the last one down here is momentum. There you go. Beautiful. Oh, so my camera's kind of like out of focus here in the corner. Oh well, you'll live. Okay, so if you need those, pause those, copy those. That's my first sheet. That's what you're supposed to do last week. So that's what I got. If you think I missed anything or whatever, you can leave comments on the band and we can talk about it and see. Maybe you guys thought of something important that I forgot because, I'm not even that smart. So, all right. This thing I posted, I want to say the first week I set up the Google Classroom. I copied this. It's on a post on there. You can look at it. This is kind of what I've been using to go through our study guide that we're making, our cheat sheet. I'm going to use this to kind of make sure we hit all the big stuff in kinematics. And then, we'll look at some of the other stuff. But this is the thing I'm going off of. It's already posted on Google Classroom. So you can go look at it and read it. But I'll refer to it and use it to fill some stuff out. Cool. All right, so kinematics is what we're going to start with. Kinematics was the very first unit we ever talked about, right? This was like, how do we say where something's at? How do we say how fast it's going? How do we figure out how fast it's going if I know where it's at some places? You know what I mean? Stuff like that. So kinematics is really talking about position, velocity, and acceleration. So let's get down all of our kinematic equations we're going to need. So the first one is x final equals x initial plus initial velocity times time plus 1/2 acceleration times time squared. Don't forget that squared. That's where 90% of people miss this problem or mess it up, is they don't square that time. That's like a math problem. Be good at math, please. Okay, so there's our position equation. Remember, you don't have to have a number for all of these. Oh no, Mr. Barton, they didn't tell me where the object starts. All right, it's 0. Just you get to pick it 0, right? You're a physicist. You can do what you want. Okay, then we need our velocity equation. So our final velocity is equal to our initial velocity plus our acceleration times time. So it's how fast we were going plus how much we speed up per second times the number of seconds we speed up for, right? So it's how fast we were going plus how much we sped up. That's how fast we're going now. Okay. Remember, velocity is the rate of change of position, and then acceleration is the rate of change of velocity. Okay. Here are some average formulas you might want. They're useful occasionally. So our average velocity is equal to the change in position divided by the change in time. This is, if you only know where you start and end, your average velocity is, if you were gonna go the whole speed the entire time, you would go this speed, and it's that speed, your average velocity. Okay, and then your average acceleration. In most classes in college, they put a little bar over it. It's called the V bar and A bar. They're averages. It's just the way math people say average. So our average acceleration is just, acceleration is the change in velocity. So it's the change in velocity over change in time. There you go. So there are the formulas I think are super important. There is one more formula that we'll put down here. This is just, if you know a lot about the problem but not the time, this is a good formula to use in those scenarios. So I've seen some things online called this like the timeless formula. It just says that your final velocity squared is equal to your initial velocity squared plus 2 times your acceleration times your change in position. So to use this, you'll notice there's not a t in here. Like there's a t there, there's a t there, there's a t there. There's no t's in this. So if you don't know how long it took in seconds or minutes or whatever, this is probably the formula you want to use. You can make this formula by solving this one for t and then plugging that into this. That's how you get that. It's a lot of work, but you don't want to do it. So there's our kinematic formulas. Now we're going to talk about some graphs because I think there's just some super easy graph stuff we want to know. So for the graphs, let's just make 2 because they're going to be pretty important for us, right? Or actually 3. Okay, so we'll make a position time graph. We'll make a velocity time graph. And we'll make an acceleration time graph. Okay. I'm going to start with the velocity time graph, just because I think that's probably the easiest one to understand. So for our velocity, let's say I'm going fast, and then I'm going to slow down to a stop. Okay. So, and we're going to do that constantly. So start fast, slow down to a stop. Try to make that as straight as possible. Okay. All right. So acceleration is the rate of change of velocity. The rate of change of a graph, that's the slope of our graph. So the slope of this everywhere, and calculus kids don't get nitpicky. You're like, well, technically the derivative isn't defined because there's not a left and right agreement of the limit. No. The slope everywhere is a negative like 1/2. Okay. So because the slope here and here and here and here is all the same, our acceleration is the same. It's negative 1/2 there, it's negative 1/2 there, it's negative 1/2 there, and there. So we just get a horizontal line, and it's on the negative side of the t-axis because our slope here is negative. Okay. To get the position from a velocity time graph, you would have to look at the area underneath the graph. You'd want to look at this stuff down here. Come on, pen. My pen doesn't want to write. All right, well, we'll use a different color. All right, you look down there. Okay. Because this is curved, you're actually going to get a curved one here. This would look like that. It'd be parabolic. So curved x graphs give us straight v graphs, give us horizontal a graphs. The slope of v versus t, let's write this down. Slope is v. Write it down here. Slope is a. Down here, the slope doesn't mean anything, but the area between the edge of your, or rather your graph and your x-axis or your t-axis, the area there is your change in velocity. There we go. And then our area here means something too. Area is change in position. Okay. So those are the three graphs I think you need to know. And you need to know the relationship between the three graphs. They're probably going to have you make some of these for some situation. Yeah, okay. Last thing we want to talk about is we want to talk about projectile motion. So things fired horizontally and at an angle, and then maybe some graphical analysis of some motion. So we'll draw some little graphs, maybe some motion maps. So if we are going to fire something at an angle, let's put like a little cannon here. There you go. So we got a little cannon. It's going to fire something at an angle. So it's going to go probably something like that. Okay. So there's our object. Couple things we want to know here. This thing is what's called free fall. And free fall just means the only force is gravity. Or weight. Weight equals mg. Okay. So the only force acting on this object the entire time is gravity, right? If we draw little force diagrams, let me see if I can get this other pen to work because I really like this pen. There we go. Okay. Would be gravity down, gravity down, gravity down, gravity down, gravity down, gravity down. So because the only thing acting on us the whole time is gravity, it's in free fall. So we want to know a couple things. The sum of forces in the x direction. So again, we're tying this back to forces because that's useful to talk about energy and work. Sum of forces in the x direction is 0 because there are no forces, right? There's nothing there. The only force is gravity. Gravity is in the y direction. So we have 0 forces in the x direction. That means our acceleration in the x direction is 0. So velocity in x will be constant. Okay. Sum of forces in the y direction are going to be just the weight. That equals ma. So our mg, because weight equals mg, equals ma. The masses cancel. So our acceleration in the y direction equals g, which is, we're going to use 10 meters per second squared down. Okay. The other things, just handy tips to know. The amount of time it takes to go from here all the way up and then back down to the same height, that time up equals the amount of time it takes to come back down. Let's just draw something like that. Okay, so to go all the way up there, T up, that's going to equal T down. There you go. So however long it takes to get up that high, if it takes 5 seconds to go from the cannon to the top, it'll take 5 seconds to go from the top back down to the same height as the cannon. So that's pretty much the important stuff you want to know about projectile motion. X and Y are independent, of course. Of course, he says, right? Obviously, who wouldn't know that? Okay, but most of this, I think, is knowing the kinematic equations. You just want to say to yourself, what do I know? What am I trying to find? Try and plug them in. We want to know the relationship between these graphs, and then just know that X and Y are independent. Free fall is when the only thing acting on you is gravity, right? Okay. All right. So let's move on to torque and rotational motion. Now that we're 16 minutes in, right? So torque and circles are basically kinematics and the other cheat sheet again. You have to know these equations, that stuff, that stuff, that stuff, but you just spin everything instead. Okay, so there is a spinning position equation. There is a spinning velocity equation. There is an average spinning velocity equation. There is a spinning version of everything, right? So I'm not going to take up half of our space just writing equations when we don't really need to. I will give you the conversion, right? So the spinning version of anything is the, so let's see, spinning equals the linear version divided by R. So we should probably define R right now, right? R is how big the circle you're spinning in is. So if I have an axis right there, and I've got a ball, and it's gonna spin in a circle like that. This distance, that's R. It's how far your mass is from this thing, which we call the axis of rotation. Okay, so you would use this kind of formula. So if you want the spinning position, right? Spinning position is theta. That equals our linear position, which is x, divided by the radius of the circle we're going in, right? So there we go. So this would actually be like how far around the circle you've gone, like 5 feet. This would be how far around the circle you've gone. Maybe this little angle right there, right? That'd be theta. Okay, so you could use this on position, you can use this on velocity, you can use it on acceleration, you can use it on a lot of things. Okay, the other important idea we want to understand for basically anything that's going to be spinning is the idea of moment of inertia. So I equals mr squared for point, point is an I, yeah, that's a cursive I. Point particles. So basically what that means is that we just need something small compared to this R. Like this, we could probably consider a point particle. If you had like an axis of rotation and we had like this disk thing spinning, because its mass is distributed near the axis of rotation, it's too close to it and it's too smushed and spread out to use this, you would need a specific formula. Okay, there are specific formulas. We're not going to write them all down here. If you need one for like a hoop or a disc or something, they'll give it to you in the problem. Okay, but you kind of want to know this because this is going to tell us the two variables we care about that determine our moment of inertia. So I is moment of inertia, which is basically a spinning mass. Right? It's how hard it feels to spin something. So if you look at this pen, it's probably like it's got metal and stuff. It's hefty and whatnot. It's probably hard to spin. If you look at like this Lego piece, it's just like a skinny piece of plastic. I could probably spin this a lot easier than I could spin that because this is bigger, right? So that one has more mass. Likewise, if you take the mass and move it towards the ends of something, it makes it feel heavier, right? We had those mass sticks that I overpaid for. Don't tell my wife about those. Anyway, we played with those, right? And we spun them. And you're like, oh yeah, they do feel different. Yeah, it's because the masses are at the end, so they feel harder to spin. So I is how hard it is to spin something. There's two things that are important here. Mass. So more mass means harder to spin. More mass, harder to spin. And then r squared. Because the r is squared, changes in radius are more important than changes in mass. If you move something twice as far, that's way better than making something twice as heavy because of the squared right there. So more radius, that means that we take this thing and just move it farther from where we're spinning around. So if you're thinking of like a merry-go-round, it's sitting on like the tiger on the inside versus like the pony on the outside. The pony on the outside has a higher moment of inertia because it's farther away. So increasing the radius also makes it harder to spin, but it's like mucho harder to spin. Okay. Sweet. So there's our moment of inertia notes. We need to talk about that. Let's check our cheat sheet so we know what to talk about. Kinematics of uniform circular motion. So everything you know about regular kinematics also applies to circular motion kinematics. The slope of a velocity, which would be omega, right? Let's maybe write down our variables. So we have theta is distance around, and it's in radians. Okay, omega is speed, which is in radians per second, and then alpha is acceleration, and that's in radians per second squared. So instead of measuring everything in meters, we measure everything in radians. That's all the stuff you need to know about circular motion, right? Uniform kinematics, dynamics of uniform circular motion, that's torque. We're going to talk about that in a sec. Newton's law of universal gravitation, we're going to put that down here, big gravity. Application, blah, blah, no, there we go. Satellites and weightlessness, we'll talk about that with big gravity. Okay, looks good to me. Let's talk about torque and rotational motion. Okay, so we need to talk about torque, center of mass. Rotational kinematics is, that was on the other thing. This is redundant. This is silly, AP board. Okay. Rotational dynamics, rotational inertia. We sort of talked about that. Rotational motion, rolling without slipping. Rotational kinetic energy, angular momentum in this conservation. Okay. That's a lot of angular stuff. All right. So center of mass is basically a balance point. It's where most of the mass is, right? So if you think about like humans, they got a head, a little neck, some arms, torso, something like that. Got some legs. Okay, the torso super big, right? Head tiny, legs tiny, feet real tiny. Look, they're just little squares. Most of the mass is here in the torso. So even though the middle of the body is like right here, like if I just say there's the top, there's the bottom, cut it in half, here's the middle, that's not where most of the mass is. Look how puny this guy's legs are. Those are like his little stick arms. His torso, he's got all this stuff filled in, and the head pulls it even farther up. So his average center of mass is probably more like there where his belly button goes or something, right? So center of mass is where the middle of most of the mass is. Okay? There's technically a formula for it. Your center of mass is, it's this stupid formula. I don't even know if it's on your equation sheet. If it's not, ignore this. It's the sum of your masses times your positions divided by the sum of your masses. It's like a weighted average of your positions based, and the way you weight it is based on how much mass it is. So there's that. Probably not on your equation sheet, probably not super important. You want to just know center of mass is a balance point. Okay. Everything will spin around the center of mass unless you like force it not to. Usually the axis of rotation goes through the center of mass. Okay. For torque, momentum, energy, they are the same idea as forces, momentum, energy. For torque, you want to draw a torque diagram. So that's basically a force diagram. Let's draw a little torque diagram here. Right. So for this, I would maybe simplify this to if it's a scaffold with a guy and a bucket sitting on it. Here's a line. We've got tension going up. We've got another tension going up, T2, T1. We've got the weight, or rather the normal force of the man's feet pushing down. We've got a little smaller normal force of the bucket going down, and then the weight of the scaffold itself. So you want to draw a force diagram, but instead of condensing it down to a point, you want to leave it spread out and look at it as like a 2D thing. Because how far it is from an axis of rotation, so maybe either the end or the middle, however far it is from that axis, that matters. So you want to leave it spread out so you can measure those distances. Okay. For momentum and energy, it's the same idea. If something is spinning, so this thing spins, and then we drop this other little thing on top of it, and then now they're both spinning together. Do you think this thing sped up or slowed down when I dropped this thing on it? Oh, it slowed down. Because this thing gains momentum, it's not spinning. Now it is spinning. Its momentum went from 0 to bigger than 0, so it gained momentum. This big one had to slow down a little bit and give it some momentum. So when this thing gains momentum, this thing loses momentum. It's conservation of momentum. So you would say that your momentum, we use capital L for angular momentums. L initial equals L final. And then angular momentum is your moment of inertia times omega, and so on, right? So I1 omega 1 plus I2 omega 2 equals I1 omega 1 plus blah, 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 right? So you set up conservation of momentum. The formula for momentum is I omega instead of mv, right? But you can use your conversion thing over here on all the variables in your momentum equation. All right, that's half an hour. All right, we're gonna power through big gravity and simple harmonic motion, and then we're done. Okay, big gravity, simple harmonic motion. Big gravity is for like planets and stuff. This is Newton's universal law of gravity. It says that the force of gravity is actually negative. This just means they attract each other. That's what that is for. It's a direction. Capital G, that's our universal law gravity constant. It's like little g, but for this formula instead, it's on your equation sheet. It's a really small number. The first mass times the second mass all over the distance between the two masses squared. And this distance is center of mass to center of mass. Okay. So this is our force formula. If we want gravitational potential energy, you just multiply the whole thing by r, so the r goes away. So UG equals negative G M1 M2 over R. There you go. Yep. Okay, so those are your two formulas. Really, it's just a matter of formulas. Let's talk about orbiting a tiny bit, and then we'll put oscillating things over here. Okay, so for orbits, let's say we've got a star. All right, so there's our star, and we are orbiting around our star. Oh, that's actually a little too symmetrical. Oh well, we'll look at it. Okay, we're orbiting around our star like that. Here we're close, here we're close, here we're far, here we're far. Because we are closer, moving close and far doesn't change our mass. So the mass doesn't change, the mass doesn't change. G is constant everywhere in the universe, we think. So the only thing changing here is the distance. At these close positions, because distance is small, dividing by a small number makes things big. The closer you are, the stronger gravity pulls. So the smaller your distance is, the bigger your force. So here we have more force. Out here, because our distance is farther, we have less force. We will come back to this idea after we talk about momentum in a sec. We'll come back. But okay. Simple harmonic motion. There's two kind of ideas they want you to know about. There are spring oscillators. So you could take a spring and you can put a box on the end, and then this box will go back and forth, right? As long as there's no friction. Okay. For this system, there is an equation that tells you how long it will take this thing to oscillate back and forth, but you have to know some information. The equation is the period of oscillation. So that's to go out, go all the way to the other side, and come all the way back to where you started. The period for this is 2 pi times the square root of m over k. So m is the mass of this box. So if the mass goes up, this number gets bigger, the time gets bigger. Does it make sense that heavy things take longer to move? Yeah, heavy things do take longer to move. Okay. K here is your spring constant. It's how stiff this spring is, it's how hard it can push based on Hooke's law. So this spring constant, the higher it is, the smaller this number gets. So this is basically how hard our spring pushes. If you push harder, does it make sense that the time it takes to move something goes down? Yeah, the harder you push, the faster things get moved. So more mass equals more time. Strong spring equals less time. Okay. The second situation you know for simple harmonic motion is pendulum. So let's say you have a ball or something hanging from the ceiling and you just let it wiggle back and forth. There's another equation for this. It's very similar. The period for a pendulum to swing back and forth is 2 pi times the square root of the length of the pendulum over little g, which is the strength of the gravitational field on your planet. Just, it's an approximation. We'll talk about how to get that from this over here. So L is that length right there. It's how long your pendulum is. So if it's really long, it's hard to move something that's far away from you on a stick. Like try and hold a 5-pound weight out with your arm fully extended versus try and hold it like close to your body. It's way easier close to your body because there's less torque. Okay. G is how strong gravity is. Notice how strong the spring is, how strong gravity is. The bottom thing is basically how strong our restoring force or the force driving the system is. So the stronger the force, it's going to pull it really hard, and it's going to swing fast. So it's going to go swing, 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 swing super fast. The stronger gravity, the less time this takes. So long equals slow. Gravity equals fast. Okay. All right, let's go patch this up a little bit. I feel like it says torque. We didn't even talk about torque. Let's talk about torque. Torque equals force times the distance from the axis of rotation times sine theta. You want them to be perpendicular. If my finger's like this, you want to push that way, not this way. Think about how's it easiest to open a door. So torque is the rotational equivalent of forces. Same way with forces, you do sum of force equations. You want to do sum of torque equations after you draw this torque diagram. Okay. All right. Last thing here. Gravity, when we orbit, will also conserve angular momentum. So here's your star. Let's make it nice and purple. Ooh, there you go, nice and purple. And now we're gonna have a weird orbit. It's gonna orbit like that. It kind of looks like a whale head, doesn't it? Okay, so there's our little object. When our object is far, let's look at just the angular momentum of this object, or the moment of inertia. I equals mr squared. And we're gonna look at our angular momentum, which is right here, I omega. L equals I omega. All right, so when this thing is moving, our planet or a little asteroid, does moving change your mass? No, absolutely not. So your mass is going to stay the same. Don't worry about that. R, though, is the distance from your thing you're spinning around. This is the thing you're spinning around. Here we're really far. Here we'd be really close, right? Very close little r right there versus right there. Okay, so if we are far, our moment of inertia is big. If we're close, our moment of inertia is small. So we know, because this is a closed system, there's just two things in it, and in space there's no other forces to hear you scream. If our moment of inertia goes up, to keep our angular momentum constant, then our rotational velocity has to change. So we said out here, I is big because we're far away. That means omega has to get small because we want our L to be constant. Here, because we're so close, R is small, I is small. That means our omega has to be large. So when you orbit, these things will go slow and come in like whoosh, whoosh, right? And they like whip around. I'm sure you're all sitting there in your chairs dying laughing. Do you hear those whipping sounds? Doesn't that idiot know there's no air in space? Idiot. Anyway, these will conserve angular momentum. So there we go. I'm sorry these notes took so long. Make sure you get a copy of them and you have to send them to me. That is your assignment for the week. If you have questions or need help with anything, please email me. If you have concerns about your grades or anything, let me know. All right. See you guys later.